Hi, my name is Bill Kinney. I'm a math professor at Bethel University, and this is the first in a series that I'm making on large and small numbers, scientific notation, and accuracy and precision. In this video, then, I'll focus on one big question here, one long question. Here it is. As of March 2012, the U.S. population is estimated to be 313 million people. Got that number off of a government website, the census.gov. Number of questions here. How precise is this number? How accurate is it likely to be? Write this number in scientific notation and put the size of the number in perspective by estimating how long it would take you to shake everyone's hand, including babies. All right, so the first question is, how precise is this number? You might also phrase that as, what is the implied precision? And so we got to look up at this number here, 313 million people. If that had been just written as, say, 300 million people, then the implied precision would be to the nearest 100 million people. If it was written as 310 million people, then the implied precision would be to the nearest 10 million people. It's written, though, as 313 million people. Therefore, the implied precision is to the nearest million people. The implied precision is basically given by the number of significant digits or significant figures in the number. In this case, we've got 3 digits that are written, that are shown, and with this phrase million people, and because of that, that means that the implied precision, the assumed precision, is to the nearest million people. So that would be the answer to the first question. The precision is to the nearest million people. And it happens that there are, again, what we call 3 significant digits. Some people say 3 significant figures. I prefer using the word digits. 3 significant figures in the number, digits in the number. There's an implication in writing that all those numbers are accurate, and we're not writing any more, so we're not claiming any accuracy beyond that, for example, to the nearest 1,000 people. That's what precision is about. What's the level of detail in the number? The next question is, how accurate is it likely to be? And that's really a harder question, and without more information, you really can't say for sure. The accuracy is related to how close is it to the true value. At any instant in time in March, there's going to be a certain number of people in the country, some true value that nobody really knows except God, and it's hard to know without more information how accurate this number is going to be. How close is it to the true value? It could be, 1,000 off, 1,000,000 off, 500,000, a couple million. It's hard to know. I got it off of a government website. Some people might claim that that means it's very inaccurate, but for the sake of argument, let's just assume that because the precision is given to the nearest million people, that means it's accurate to within 500,000 people. I'm making an assumption there when I do that. It's really based on the process for how the number was obtained. So I'll just say, assuming the process for how the number was obtained is good, a good process, then it's probably accurate to within, if it's precise to the nearest million people, we'd say it was 314 million if it was closer to 314 million, or 312 million if it was closer to 312. So it's probably accurate to the nearest 500,000 people. because we're rounding to 313 million. So it's probably accurate to within, get rid of that G there, within 500,000 people, 500,000 people. I'm making an assumption there, assuming the process was good. I'm not going to go into what that means. You might want to write that as a percentage, a relative accuracy as well. And if you did that, you'd have to take the 500,000, 500,000, and divide by 313 million. And if you write that out the long way, you write it out like that. And then if you use your calculator to do that division, to find that fraction, $500,000 divided by 313 million gives you 0.0016 approximately. 0.0016 as a percentage, that would be 0.16%, about 1/6 of 1% if the method, the process for obtaining the number was good, so to speak. So that's accuracy is how close is it to the true value. The true value really is unknown, so you really can't say for sure how accurate it is, but you might say it's likely to be that accurate, what I just said there. All right, the next question was put the number in scientific notation. Written out, again, the number was 313 million people. Supposed to be a P there, people. In scientific notation, you're writing it as, well, in this case, you'd take the first three numbers, the significant digits here, and put them, make them like this, 3.13. Put the decimal spot after the first non-zero digit. And then you multiply by an appropriate power of 10 that will make these two things equal. And the way to figure that out, one trick, is to imagine a decimal point right there and ask yourself how many places do you have to move the decimal to the left to get it so that it's right after that first three there. 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8th is what you need to multiply that by. 3.13 times 10 to the 8th people is the way to write the population in scientific notation. We still see that there are three significant digits implied by writing 3.13 here. And if you enter it on a calculator like that, 3.13 times 10 to the 8th power, see that? It spits it back, written out the long way. Some calculators represent scientific notation in the following kind of way. On this kind of calculator, you see above the comma there, there's an EE. If I hit the second function and press that button, it makes one E up there. That E stands for exponent. If I type it in like that, it is representing it internally as 3.13 times 10 to the 8th power. You can see it's the same number. And sometimes you'll see your answer spit out like that with an E and a number after it, the 8. This is saying 8 is the exponent of a power of 10, 10 to the 8th power. 3.13 times 10 to the 8th is the calculator's way of doing that sometimes. So that's how it is in scientific notation. The final thing to do is to put this number in perspective by estimating how long it would take you to shake everybody's hands, including babies. And so you need to roughly estimate, if you were sort of consistently, continuously shaking people's hands, maybe it takes you about 5 seconds to shake somebody's hand and nod at them and then go on to the next person. If it's 5 seconds per handshake, 5 seconds per person, what you would need to do to figure out how long it would take you to shake everybody's hands then is then multiply these two numbers, 3.13 times 10 to the 8th, or 313 million people, times 5 seconds per person, The people and person cancel. It doesn't matter that one's plural and one's not. And what are you going to get? 3.13. I'll type it in there with an E. Multiply that by 5, you're going to get over 1 billion seconds. That's 1.565 billion. 1.565 times 10 to the 9th seconds. Technically speaking, if I was going to write my answer in terms of seconds, there's only one significant digit there, and so I should round my answer to really one significant digit here, 2 billion seconds, but I'm going to ultimately convert this to, say, years, and I'll just round to the nearest year at the end, and you don't want to round too early or else you'll lose some accuracy. How many years is that? Well, since there's, I'll just do it with the calculator here, since there's 365 days, oh, excuse me, this is seconds. Since there's 60 seconds in a minute, if I divide by 60, that's the number of minutes. Since there's 60 minutes in an hour, if I divide that by 60, I get the number of hours. And I made a mistake there. That's the number of hours. If I divide that by 24, I'm going to get the number of days, since there's 24 hours in a day. And on average, there's 365.25 days in a year. It's going to take me approximately 50 years, if I round to one significant digit, to shake everybody's hand. So that gives you a little bit of an idea of the size of the number. If you're shaking somebody's hands 5 seconds, every person, it's going to take you that long to shake everybody's hand.